time to have even more fun than a student should be allowed to have. Building what? No, I could change variable. Build quadratic models from verbal descriptions of data. I think you could take your data, Nolan, that you have for your fantasy football and apply these skills to it, and it might help you. Okay. See, the thing is, what we're looking for here is, maximum or minimum, an optimization. Maximum revenue. Now it says, marketing department at TI has found that when certain calculators are sold at a price, the number of X calculators sold is given by demand. Okay? Find a model that represents the revenue as a function of price P. Well, what should we look for? What is that formula giving us to us? What kind of an equation is this? X calculator sold is given by the demand equation. So this is asking for demand, right? If we set the price at a certain number, then the demand for that is this value of X. So if we take a look at the next equation down here, just talk about the model down here. Revenue. Well, that's how many people buy the calculator at a certain price, correct? Do they tell us what the price is? No. But they do tell us how many people will buy the calculator at a certain price, correct? So that's where the X and T comes. So if you take a look down here, they end up having 21,000 minus 150P multiplied by the P. So this kind of goes back and takes a look at question B. Sometimes I always like looking at this before I try and come up with a model. What's the domain? What are we really talking about here as the input variable? It is the price. It's not the X like we're accustomed to seeing. It's the price. That is what is going to determine whether or not the calculators are purchased. So that kind of gives us this idea that, hey, we should be looking at P as our input rather than X. Just a way of looking at it. So now that we've got the function identified, the rest of it's pretty easy. We can drop that into the graphing calculator. We can go through and do the math on it. We can see the graph on it. We see this. So they're saying that if they go and price the calculator at $70, that they are going to make a revenue of $735,000 at a price point of 70 calculators. Does it tell us how many people are actually going to buy the calculators? Well, we could look at that someplace else, put in the price, and if we take a look at that up here, we put in the price, we find that there are 10,500 units sold. So we would be able to go and take a look at that and figure out how many calculators we actually would have to buy in order to maximize our revenue for this particular calculator. Sort of kind of makes sense? I mean, it seems kind of counterintuitive at times. Well, you're looking at, well, how many people are going to buy the calculator? That's what we're really concerned with. But take a look at it in terms of gas prices. Gas prices are dropping, yes. Do people tend to travel more, drive more when the gas prices go down? So the demand for fuel is identified by the price of the fuel. Then people are more apt to go someplace. Kind of the idea that we're looking at here. Susan, what were the other questions that they're asking for here? Graph R, what price should to collect at least 675,000 in revenue? Well, if I wanted 675,000 in revenue, then I can put in my line at 675 and look at the intersections there. So, if you had a price point of 50 calculators, you could still make that money. Or if you had a price point of 90, you could still make that money. And you're kind of wondering, why in the world would you want to do that? Say, for example, that you wanted to have it, you had a projected price or projected profit, revenue, based on this. We need to make sure that we see at least $675,000. Now, if I price it at $70, great. But what happens if I want to, generate a little bit more interest in this? Okay, when do calculators get involved? Okay, so we could be looking at, say, the end of August, the first part of September. What happens if I wanted to had my price point at $70 for the calculator, wanted to generate a little bit more interest on it? I still need to make sure that I make $675,000. What could I do at the beginning of the year to help push that forward? To generate that interest? What? Lower the price. Would you want to pay more for the calculator that was $70? Hey, this week we are selling our TI-84 graphing calculator, regularly priced $70, is now on sale for $90. That really wouldn't work very well, would it? But if they said our $70 calculator is now on sale for $50, does that help encourage the sale? It moves it along. Granted, $70 is maximum, but even if they had set it at $90, now think about this logic. What happens if the price point was $90 and they wanted right up by at end of August, first part of September, they dropped the price down to $70. They make it actually more money. So if you think about it, if they set a price for their product at this place where they will make what their projection is for this particular unit, they choose the $90 price point, they get what they want, they drop it down to $70, they can even make more off it. So when you see a sale on there, could this be a potential graph for that type of revenue? That's a heck of a model, and to be honest, I had never looked at it this way until this. Set the price point at what you want to get back, and if you drop it, you can even generate more interest, make even more profit off of it. Because generally you think about that if they put something on sale, they're losing money, right? We just created an instance where they're actually making more. Interesting thought. So, now these are always fun. Maximizing the area enclosed by a fence. Yeah, I think that we did that one in here. We had the rectangle and the triangle. Yeah, same idea. Farmer has 2,000 yards of fence to enclose a rectangular field. What are the dimensions of the rectangle that encloses the most area? Okay. Not a problem with that. We find out that it actually turns out to be 500. Remember when I said that that on a given perimeter, maximum area is always going to be a square? I talked about that when we were doing that problem with the playpen or whatever. So, analyzing the motion of a projectile. Something you probably would have liked to have done about 2 weeks ago, right? Projectile is fired from a cliff 50 feet above the water at an inclination of 45 degrees to the horizontal with a muzzle velocity 400 feet per second. In physics, it's established by a wonderful thing. Okay? So if your deer is at 5,000, what's the label on for the X? What's X? I don't know, read the problem. Where X the horizontal distance. So odds are we're probably in feet. 5,000 feet, almost a mile out. 500 feet above. If you wanted to hit that, that means you'd have to aim for that point up on top there, right? You have to set your angle up. You wouldn't be shooting at it, you'd be shooting above it. Back in World War II, they had rooms full of people, calculators, and we talked about that. And they were actually calculating out ballistics tables for various firearms, various guns. Well, yeah. Well, yeah, you got distance out there. I mean, you even have to start taking, once you get really far out there, you got to take into the rotation of the earth, rotation and curvature of the earth. I mean, that's some good math. So all of these things here are creating models for us to go through and figure out and answer questions. Golden Gate Bridge is a suspension bridge, spans the entrance to San Francisco Bay. 746 foot tall towers are 4,200 feet apart. Bridge is suspended from two huge cables more than 3 feet in diameter. The 90-foot roadway is 220 feet above the water. The cables are parabolic in shape. Okay. It actually goes down there and talks about that, but we will deal with that. Touch the road surface at the center of the bridge. Find the height of the cable above the road at a distance of 1,000 feet from the center. Now, we're given this information. Remember me saying a picture paints 1,000 words. Always go out and try and draw this out. Now, it doesn't matter how you draw it out. It matters that you draw it out. Now, it makes calculations a lot easier if you set your vertex here, but I could have just as easily set the vertex over here and identified my numbers as well. It doesn't matter. Once you've got the information, you've got a vertex, you're able to identify coordinates for points on the parabola. There you go. You can use that to build an equation. You can pop it into a graphic calculator, tell it to do a quadratic regression. Use the stuff that we learned a couple days ago, put in the vertex on it, put in one of the coordinates, and solve from there. Now, the calculator really comes in handy when we need to do this kind of stuff. You'll notice that the points there really don't look close. Kind of like a check mark. Yeah, you got that curvature in there. That could possibly even be, how your team is doing in fantasy football as it progresses throughout. You got, slowly. So, Nolan, I assume, Nolan, that yours is looking like A. You'd rather have it look like B, right? Well, we're still going down. We're early in the season. That's okay. That's okay. But you've got your data there. You can plug that, all of it in. We use the stat plot just like we had done before with a line. Use the stat plot. And then we can use what's called a quadratic regression. It'll take into account all of the points, give us the information back. And again, always go back, put your equation in that you get to the data and take a look at it. Now remember, if you want to go and turn the diagnostics on this thing, you can go and do that. That'll kind of help. But that really only works for the linear. Okay? There are some things out there that'll give you it's kind of close fit. But the R doesn't work here. That really only works for the linear. Okay? say it's, well, r is derived from r squared. Okay. So, or r squared is derived from r, but no, it's the same measurement, just in a different way. So, there you go, and I'm going to let you have start working on this stuff.